Hello and welcome to the review for exam number 2 for GIS 200. I'm going to go through the material somewhat fast, but I'm going to cover everything that could potentially be on your exam, along with some essay questions at the end of the slideshow that might help you. Listen to it all, then listen to it again, and use this as a supplement to the notes you've taken in class and the things that we've talked about. I'm sure you all do quite well. So, what are the two types of coordinate systems, unprojected and projected? Know that on maps you can have multiple different coordinate systems at the same time, showing where things are located, particularly on older printed maps. Understand that in order for data to be displayed, in order for data to be spatial data, it has to have a coordinate system. It can be either projected or unprojected. Sometimes it's not labeled, but it always has a coordinate system. There are, excuse me, 5 components to a spatial reference: the geographic coordinate system or the datum, the projection, storage units, the domain, and the resolution. Know a little something about geographic coordinate systems. Know how you measure longitude and latitude. Longitude being angular degrees around the equator, and latitude being a north or south distance from the equator. Geographic coordinate systems are measured in angular degrees. Do not tell me they're measured in degrees, minutes, and seconds, because they could be in decimal degrees or decimal minutes or anything, but they're all angular degrees. The reason we don't use unprojected data, because unprojected data requires a lot of high resolution in order to be accurate. 1 degree in a decimal degree system is equal to 110 kilometers. Now, what an ellipsoid is, that the fact the Earth isn't round, it's really sort of smushed on the top and bottom. It has 2 axes, a major and a minor. Minor being the short one being the one that the ellipsoid rotates around. A geoid is actually more that true surface, that theoretical surface, defined by gravity measurements and all that. And so it's kind of that topography that we actually deal with. A datum is simply the mathematical fit that we create, where we move the ellipsoid around so that it better fits the geoid. And we define a datum by the particular spheroid that it's based on, and the adjustment or fit that we use to make that particular spheroid fit the geoid. Some common datums used in North America: NAD 27, NAD 83, NAD 83 Harn, WGS 84. Projections and datums: every projection has a geographic coordinate system. Every geographic coordinate system has a datum. Therefore, every projection has a datum. Projections based on different datums will be offset from one another because it's the definition of the datum. It's a different fit of the base coordinate system. The amount of offset depends on where it's at, typically around 300 meters. Transformations is what we do when we convert from one datum to another. They are purely a mathematical exercise. The problem is that they do create some errors, and so you don't want to string together several data transformations. You want to stick with as few of those as possible. Predictive coordinate systems is what we do to take the nice round globe and create the flat map. 3 basic types of projections: cylindrical, conic, and azimuthal. These are some examples. You can see how cylindrical would be like Mercator or transverse Mercators when the cylinder runs in the other direction. Conic, things like Lambert conformal conic or equidistance. Azimuthal are where you literally just see the plane like that touching the surface of the globe. Every projection has various parameters like the false easting, false northing, central meridian, standard parallels, etc. Central meridian is that line of longitude that serves as 0 or the origin on a map. Reference latitude typically is the equator, is the one that we use for the other measurement. When we look at these projections, they occur in one of two conditions, tangent or secant. In this example, we're looking at a cylindrical projection, and in the standard or the secant. In the tangent condition, it essentially touches the globe on one plane or one line around the planet. When it's in a secant configuration, the cylinder is slightly smaller than the Earth, and so it intersects the surface, thus having 2 points where it perfectly lines up, and those are then the standard parallels as opposed to the standard parallel. False easting and false northing do nothing except arbitrarily change the numeric values of the coordinate system to eliminate negative numbers. Coordinate units are the units that you work with. When you project data, it changes the XY values from degrees, angular degrees, to some linear measure like meters or feet. All projections introduce distortion. The type and the degree varies by projection, and so when you select a projection, pick one that is most suitable for what you're trying to do. Some projections are actually what we call compromise projections because they distort everything a little bit and nothing horrendously. The extent is simply the coordinate range that covers the data set that you're looking at. And so if you have a global data set in this example, that would be the range. Raster coordinate systems, you got to know two things. One, the coordinate of the upper left cell in the raster grid, and then the shape of the features. That's pretty much what you have. Raster coordinates, South Dakota topography in two different coordinate systems. One is in a projected coordinate system, one in geographic. Notice how geographic looks weird. It's because the distances between longitude and latitude vary at different places on the Earth, and that leads to significant distortion. Local rasters, if you look at something that's in something like UTM Zone 13, it would look like this, but if it's in a state plane system, it would look slightly different because of the projection. If a raster data set is prepared to already be used in GIS, if it is spatially coordinated, and the software can identify where it's at, then it's geo-referenced. This is some examples of things that would be geo-referenced in. I'm not going to go over this too much, but basically, if things are off, you have to go through the process of geo-referencing them, where you identify like locations or known locations that you have the coordinates for, and input that so that you can correct the image. The next step is rectification. That's where you permanently transform the image into a new coordinate space. There's multiple ways of doing that. We measure how well we did that with something called the RMS error, or the root mean squared error. It is the residual or the difference between the predicted value at each known location after the rectification compared to what we know those locations to actually be. So during rectification, you have to go through something called resampling. You have this new grid spacing, and so you have to figure out, once you have the grid created, what the values are, and it does that by looking at the values. That does that using one of three techniques. We went over this in class a ton. Nearest neighbor, bilinear resampling, cubic convolution resampling are the three techniques. Like I said, you can read here exactly what they do and how they work, but just make sure you get this. Nearest neighbor looks at the four closest cells. Nearest neighbor looks at the closest cell and uses that value. Bilinear takes the four closest and uses a distance weighted algorithm. Cubic convolution does the same thing, but except it looks at 16 cells. Again, cell centers, linear distance weighted algorithm. Projecting rasters is a lot like projecting vectors from one coordinate system to another. By projecting it, cell centers are converted into a new system, so the spacing changes, and after that you just have to resample it if you're going to rectify it, and then everything looks great. Common projection systems. Most common ones are the geographic coordinate system, which is typically degrees of longitude and latitude, and that is because that's the way a lot of data is delivered. UTM is also a very popular one. It divides the world into 60 zones. The state plane divides each state into one or more zones. Larger states tend to have more, and that's the three most common systems that you'll deal with. Geographic coordinate systems are primarily used for data distribution. They're not desirable for mapping because it creates distortion, and they should never be used for analysis. The UTM system, it's an important one, divides the world into 60 zones, 6 degrees wide. It does this because it's a transverse cylindrical projection. So you take the cylinder, instead of running it north-south, you run it east-west. Thus, when you rotate it around the minor axis of the ellipsoid, that zone, or the center of that zone, moves, and wherever it's at, obviously within a certain distance of that, it's a pretty accurate projection. Turns out that when you make 60 zones globally, 6 degrees wide, using this idea of rotating this transverse cylinder, it does a really good job. State plane systems based on areas with unique identifiers, something like a FIPS number, and the state itself decides what's the ideal projection parameters for those locations. And there's a ton of them out there, all different kinds of stuff. Here's a map of them. How do you choose projections? The answer is very carefully. Alright, so how do you select them? Never use a geographic coordinate system for a map or an analysis. You want something that works for what you're trying to do. You pick between cylindrical, conic, and azimuthal to try to find the one that preserves the properties that you need, whether you're looking for something that's north-south oriented or east-west oriented, or in the polar regions. Each one will have a type of projection that is more properly suited for. Also look at the scale. Are you looking at something local like a city or county? If so, projection systems virtually eliminate the distortion. And so UTMs or state planes work really, really good. But your map needs to lie within a single zone or a single UTM zone or a single state plane zone. Small scale areas, in other words, really, really vast areas like continents and countries, distortion is inevitable. So you have to choose one that does not distort the variable that you're interested in, or you select some sort of a compromise or conformal projection so that you don't overtly distort any one thing very, very much. Lots of problems in solution work here. Probably could have took these out, but it's worth going over again. What do you do if it doesn't line up? The state is not in one UTM zone. You shift to UTM zone. You try to create a new one for the entire state from a state plane. You take the state plane, you change the parameters so it fits better for the entire area. This is the best example where we created a projection for Turkey using a conformal conic Lambert, and then we set the various properties, central meridian and the two standard parallels, so that it would be more well suited for Turkey. And then we saved it as a unique one. Now, the problem is, if you do this, it makes your maps better, but it does create other problems. You need to convert all your other data into that system. You won't be able to use a GPS unit to collect coordinates in that system, so you have to collect them in something else and then reproject them. And non-standard projections means you need to be really good with your metadata because other people are going to look at it, and it's important that they understand what you did. Labeling coordinate systems. Coordinate system labels. It's got to have all that stuff in place for catalog or ArcMap to know what to do with it. Labels always have a geographic coordinate system because every coordinate system is based on a geographic coordinate system. And we also have a projection and its parameters if one is used. Spatial reference is the geographic coordinate system or the datum, the projection, the storage units, the domain, and the resolution. You really know that. If data is projected or unprojected, you can look at the source tab and get an idea of that. And sometimes you can tell if it's messed up by that by simply looking at what you have. And if it's supposed to be in a geographic coordinate system and the numbers look like they're in decimal degrees, then that makes sense. On the fly projection. Big thing you need to know with on-the-fly projection is it does not project anything. It simply allows you to display data that is in multiple projections at the same time in the same data frame. That's all. It's a wonderful thing. It allows you to take data that's in UTM, some it's in geographic, and some it's in state plane, and display it all together, and it works fine as long as everything is in the same data. Storage units are the units associated with the data itself. Okay, you can set these from the data frame properties. You can also change the map unit display, which is different than the actual map unit. Don't get these things mixed up versus the map versus what you see. That's kind of a problem. Projecting data. If you have data that needs projected, it's not that big of a job. Permanently project it creates a new shapefile. If you're trying to permanently project something and you don't get a new spatial data file, you use the wrong tool. You can do it using the project. If you're talking about rasters, it's a different tool, the project raster. Troubleshooting coordinate systems is really part of the job. Something's displayed together, but it's off by something. It's usually a projection issue. Could be something mislabeled. Could be a different. Two data sets should map on top, but they don't. What do? Well, you check to see if something's missing, and then you check to see if something's wrong. If something's missing, you simply add that in. If you don't know what it is, you use process of elimination and multiple choices to keep working through options until things are displayed the way they're supposed to be. If it's undefined, that's how you fix it. If it displays correctly, it's probably in the layer that your other data is in. If it doesn't appear at all, then you have to define the coordinate system somehow. You can look at the extent to get some idea of what that might be based on the numbers. Ultimately, if you need to fix it, once you get a coordinate system labeled correctly, then you can use the define projection tool to project it however you want or to change it. If something is labeled but it's simply labeled wrong, then you want to use the a different tool for measurable data. In order to fix it, you're going to use the define projection tool, not the project tool, the define projection tool. Don't confuse these. Very different tools do very different things. Notice the flashing caution. That's just to make the point. Okay, here is some slides that basically just give you an example of the reasoning behind this. I'm not going to go through all these, but you can take your time and go back through them on the slide. Okay, I'm going to go over this just a little bit. Define projection and the project tool. Define projection changes the coordinate system label, doesn't change the coordinates, keeps the original data set. The project tool changes the coordinates, changes the definitions, creates a new data set, permanent changes because it's something new. Geo-referencing raster. Okay, download an image like this, go through the process. This is sort of a very short demonstration of that. Decide on the coordinate system. The output image will have, obtain a reference layer with points that you can match, load both of them into ArcMap, establish your links, and then update the geo-referencing. That is all you have to do to explain or describe that process of geo-referencing. Remember, images and maps. The map and the image does have some sort of a projection. And this is showing how you can prepare your reference map, but there's also other ways to do that as well. This talks about the process of adding links. I'm not going to ask you a lot of questions about this. The big thing is to remember the add link table and how you can add the links and then look at the root mean square error to get an idea of how good your fit is. You may have to select a particular transformation. Start out with the first order one like affine, and then you move to a second order like a polynomial or a third order polynomial, all depending on how difficult or how much bending and stretching you have to do to make the transformation. When you're doing this stuff, zoom in and add as many points as you need. Once you get something that looks pretty close, then you can go examine the overall registration, and then you can confirm. And do one or two things. Finalize the geo-referencing, basically just updates it. It stores the transformation parameters in a file with the image so that when you view it, everything works. It keeps the original image, and it just positions it based on the fly as it's displayed. Or you can rectify it. That produces a new image. It's a permanent transformation. That can affect the image color, so because it has to resample when it creates a new one, so it may make your pictures not look as bright or as detailed. Symbolizing stuff. Different shapes, different sizes, different thicknesses, different types of lines, different colors, different patterns, different fonts, different size fonts, different color fonts, different styles of font. All these are things that you can use to differentiate how you display or represent data. Color. It's used most frequently way to show differentiation. Depending on what you're doing, you might want to go with a single color ramp or a complex multiple. When you're selecting symbols for maps and you want them to be effective, there's a couple of things you need to consider. One is the convention. In other words, what is the standard practice? How do we represent this? Using, for example, like little red crosses for hospitals, or doing a temperature map with blue being cold and red being hot. You need to think about things like connotation, about the idea of what the data or what the map is actually saying to you subconsciously, like ocean water should be blue and the earth should be brown, not the other way around. And then you have to think about things like color blindness and make sure that you're making maps that people who have some sort of visual impairment can still use. Rainbow ramps rarely work well on polygons. They're better suited for continuous rasters. The best way to make a good black and white map is to make it as a black and white map and not make it as a color map and then let it simply be printed in black and white. You should never do that. When you design in black and white, a couple of things to keep in mind. No more than 5 levels of gray. Consider using patterns instead of colors. This is an example. Sometimes we have to normalize data. This is an example of normalizing data. Looking at number of farms in each state. If we normalize it by square mile, it gives us a much better idea of just how many farms there are per area. Takes us to a little problem we come across sometimes, the modifiable area unit problem. You need to know what it is. You need to understand it. It's when we have arbitrary aggregation units like states and counties and how that can influence the numbers and the things that we map. The number of farms, for example, is affected by the size of the state. So the number of farms isn't that terribly useful, but we can normalize it to number of farms per acre, and then we can work around some of that. The number of vacant houses is affected by population. It's also affected by the total number of houses, because is it a percentage of the houses that are vacant we're interested in, or just a raw count? And again, those numbers will be affected by the size of the area that you're aggregating upon. And that's what the modifiable area unit problem is. How do we minimize it? We normalize it. Just another example. We can also have visual map. Basically, it's the same thing, modifiable area unit problem, except it plays deeper into your psyche in that the visual apparatus in your brain looks at those aggregation units, and what happens is larger polygons tend to dominate your maps, and they attract greater attention. So we can work on that by using things like graduated symbols or dot density maps to help overcome that. Types of rasters. Two generic types here we're looking at is discrete and continuous. You can read exactly what they mean. As far as other types, there is also thematic and image. Thematic being some sort of theme, things like rainfall or land use, and image rasters being, of course, images like satellite photos or ortho photos shot from aircraft. Raster pyramids, not built in Egypt. Pyramids are used to speed up the display of rasters by creating successive low-resolution copies. So as you zoom in or out, It uses the most efficient layer to give you the current visualization at your extent. And so once you create them, you can use them over and over and over. It increases the size of the file by about 50%. Slicing is one way that we apply colors to rasters, where we simply look at what's the lowest value and what's the highest value, and we bin the numbers up based on how frequently they occur, and then use that to assign colors. Stretching is a little bit different. We know that the stuff we're really interested in is occurring in the middle. So we identify some volume of our data that is either very high or very low, and based on this selection, we basically lump all that stuff at the ends of the distribution together into the single low and the single high, and then everything else in between is allowed to be spread out more, and it makes a lot more sense publicly to look at it. Sorry for that long pause there. I was trying to remember exactly what I was wanting to tell you about this else. Again, bin up the numbers at the high and low, stretch out the stuff in the middle. It's called stretching. Whatever else I was trying to think of, apparently it wasn't that important. This gives you an idea what some of these images look like as opposed to when they're stretched or used as standard deviation as opposed to not using anything at all. Another example. Red, green, and blue composites. Some raster images have colors in multiple bands. Bands combined together to give you a color image. Different combinations of band give you different images. Classifying data. You need to know these 6 types of classifications and how they actually work. Jenks natural breaks is the default. Exploits natural gaps in the data. It's good for unevenly distributed or skewed data. It does this by selecting the various classes so that the standard deviations in each class, when averaged together, gives you the smallest possible value of any group of combinations. Equal interval is on equal intervals. Shocker. Defined intervals are ones of a set rate, like every 10,000. Quantiles based off of count and distribution, where you have going from low to high starting out, and you group a certain number of values together, and then the next number, and the next number, and the next number. Geometric interval is a math-based calculation. Standard deviation is based off of a statistical model. Dynamic labels is something you can turn on and off. They can be redrawn when the map view changes. You can adjust how and where they're placed, and whether or not you can even see them at certain degrees of zooming in or zooming out. You can do a lot of this stuff from the Labels tab and layer properties, as well as the placement. And from the placements, you can select where you place it, and how you place it, and what they follow, and how they follow it, and the range when it can be seen and not seen. And you can do some of this from the labeling bar, where you can go in and assign symbols like points, lines, and polygons. You can also use styles. Pay close attention. Styles are groups of symbols stored together. It sounds like a test question. There are just different types of maps as well: single, unique values, quantiles, charts. You need to know a little bit about those. Normalizing data. This is just an example of how you can use something like square miles to normalize the number of farms to get a farm density number, which helps avoid map. Classifying data. Again, you need to be able to explain in some detail what each of these mean and how to classify it, how you can exclude some data from that, and how you symbolize rasters, unique values, discrete colors, or you can classify, use the same techniques we've been talking about, things like Jenks natural breaks. You can stretch the value. You can display them as single image bands or multi-bands, depending on the data. One of the basic principles of map. You're going to get this as a test question where you'll have to fill in those boxes. So memorize this, please. What are the important steps? Know the four. What's the purpose? Who's the audience? What's the medium? How's it going to be viewed? How can you use maps? Location, navigation, compiling, convincing, comparing, analyzing. Who's the audience? Who will be viewing it? What's their level of knowledge in the subject matter or even maps in general? Do they have special requirements? Is anyone colorblind? At heart of do they have poor eyesight? That kind of thing. Is it going to be paper? Is it going to be electronic? Is it going to be on a computer screen, a mobile device shot out of a projector up against a wall? You want to make maps for the way that they're going to be viewed. So, make maps for the medium. Is it a poster? Is it on the web? Is it something that they're going to study for a long time? Or is it something that has to catch their attention? Understand these bullets. Memorize a few of these things. Again, select. You got to make maps that tell good stories, so you need to get good data, and you need to label and design and symbolize things so that people understand it, and make sure it's not too busy so that it distracts or obscures what you're trying to show. Be cautious with personal information. Don't make largesse claims, particularly if it has the penalty or the possibility of creating economic penalty on others. You want to be careful of that. Selecting within layers, there's different ways you can do that. Sometimes you need to simplify data, and so you can use something called cartographic generalization, where we just sort of make something that is similar to something else for purposes of mapping. We can do this when we have to adapt back and forth between large and small scale data. You can also query stuff. Some examples of generalization, things like aggregate, collapse, and displace and typify and reclass. When you're going to select a projection, there are other things that you can do as well. You want to select a projected coordinate system, not a geographic coordinate system. Different types of projections: cylindrical, conic, azimuthal. Unintended consequences: projection choices may affect the story. Certain maps display or distort certain things, and so the maps that you do make other things very difficult to understand, and it can be misleading. For example, this particular projection causes things like Greenland to look almost the size of Africa when it is in fact nowhere near that large. Maps should tell a story, and you should be able to tell what it is, and this is a situation here where you cannot. North arrows work good for some projections, but when you have a conic projection, realistically, if you're looking at a large enough area, you probably need gradical grids because they show you the true north direction where a north arrow does not. There's other types of grids, measured grids, for things like UTMs, so that you can see what the coordinates are, and you can have reference grids so you can identify places or parts of a map, like for example 4C, the section that would be identified by the 4 and the C areas on the map. Arranging data. Visual hierarchy. In order to perceive what's going on, the different objects in the map, you put them together in a certain way so that the important stuff looks in the foreground and other stuff that's not important stays out of the way and doesn't ruin your maps. This is an example of a map. You can see some of the stuff. What is the map about? What did you notice first? Where did your eyes move? How was the path achieved? That's what visual hierarchy is all about. We do this with the visual center, the rule of thirds. We use it with balance and negative space and alignment, neat lines, symbolization, color, contrast, size, thickness, foreground, and background. It's all the things that we can put together to establish the rule of order on a map. Visual center is higher than the geometric center. Rule of thirds tells you that the important thing in the photo should not be placed in the center. It should be placed near one of those circles there on the bottom left, at some place like that, allowing the other parts of the image to serve other purposes. Alignment, you want to keep things aligned. You don't necessarily have to use the neat lines, but you need to space things up using columns and edges. You want to have some negative space, but you need to balance it. You don't want to crowd things, but you don't want to leave too much open. Sometimes you have to change your map design. Subtle changes can make things look really, really good or look very, very poorly thought. You want to balance your elements. Symbolization. Think about these different ways that you can symbolize things and what stands out, what catches your eye. Remember, there's lots of ways to represent stuff, and you just got to figure out what's really good for what you're trying to show. Visual hierarchy, a good example here is that the grids should be behind the mapped data, not in front of it. And you can see how that looks very different when you place that in the wrong spot. Base maps are really good to help you see things, but they belong in the background. They should not distract or detract from your other data. Once you make a map, you need to check the balance, the hierarchy, the colors, see if it's going to print right, look for errors in spelling and grammar. Did you put on the sources and that kind of stuff? You want to review it and edit it and make it better and then try again. You want to pay attention to detail. The little things like good formatting help a lot. After you're done, you make a map like this, you review it, you pick out the things that aren't very good, like the funny spacing in the text box, the size and the lousy abbreviations in the legend, the excessively dominant drop shadow on the title, that kind of stuff, and fix it so that you get something that looks more like that. You can also go to an external review where you have people who are familiar with the subject matter or people who are similar to your intended audience. Look over your map product and see if you can come up with more information that you need to change or fix or design, things that you can do to make your design better. You edit and improve your map using these 4 simple steps. Concentrate on the message. Simplify, 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 simplify. Don't be afraid to experiment, changing things around. Always test your map under the conditions of use. So look at it, how it will be looked at in the end. And then once you've done all that, you're almost done, usually. Map layouts, this is just one example. The more complex the material is fine if you have a more complex audience that has a deeper level of understanding. So you have to make the maps that meet what people need, and the things that you include in map layouts include the map, place titles, legends, scales, north arrows, tables. You can add images and logos as well. Here are the steps to creating a good layout. Some units that you need to remember. Map units are determined by the data frame. Display units can be set. Page units are usually what we were talking about is how the map itself is placed on the sheet of paper. Dynamic labels, graphic text, and annotations are all different types of labels. Dynamic ones are ones that are placed automatically. Graphic text are simply text boxes that you place on the map where you want and edit them. And annotations are created for dynamic labels, and they're saved kind of like a... Think of it like as text box pretending to be shape files or point data. Just more about where you go to set this stuff up, what it looks like, how it can be set, the various tools that allow you to modify things, same with annotations, default label scaling, scale, and how you go about creating annotation and creating an annotation. Overflow annotation, when you do annotation, sometimes there are things that are on the list that just don't make it on a map. They go in the overflow box where you have to individually decide if you want to leave it there, delete it, or put it back in place. From the data frame properties is where you place in grids. Grids and gradical grids have their own little wizard to make sure that you get exactly what you're looking for once you start making grids. When you go to print your map, look at the setup, check everything out, make sure the spacing is proper, and then print a draft. Oftentimes, remember, labels and things like that, colors are going to come out a little different. And so what looks like a perfect map on your computer screen may not print like a perfect map. You can also export your map as a picture file instead of exporting it as a printed map and printing it. This allows you to do a lot of things with it. Alright, so I said earlier that there were some questions, essay questions in the exam. So I'm going to go over the next sort of 12 slides that are going to talk about topics. And these are the things that you could potentially be asked essay questions about. Number one is the type of coordinate systems. If I ask you what they are, you should be able to tell me about unprojected and projected coordinate systems and what they actually do and what they are. Same way for a spatial reference. You should be able to tell me what the 5 components of that is. You need to know what a geoid is and how that relates to a spheroid and how that relates to a datum. You should be able to tell that entire story like we went over in class. You need to know what datums are commonly used in North America. Now, I'm not going to ask you which datum was based on Clark's 1866 spheroid. No, I'm not going to do that, but you should be able to recite this list of NAD 27, NAD 83, NAD 83, HARN, WGS 84. You need to be able to explain the 3 basic types of projections and the 2 types of conditions that they exist in. In other words, cylindrical, conic, and azimuthal, and secant and tangent would be the conditions that each of these types of projections can exist in. You need to be able to explain this. You need to be able to explain this resampling thing. You need to know the 3 resampling methods and explain the difference between them. Which is the fast one, which is the slowest one, which gives you the sharpest detail, which one, you need to know those things. You need to basically understand and be able to recite the majority of what's on these paragraphs. But just for the heck of it, I'll go over them again. Nearest neighbor basically finds the cell value at the center of the previous cell closest to the new one and uses that number. Bilinear looks at the 4 closest cell centers and then does a distance-weighted algorithm to come up with a new value for the new cell. Cubic convolution does the exact same process as bilinear, except it looks at 16 cells instead of 4. Nearest neighbor is the fastest, cubic convolution is the slowest, bilinear is somewhere in between. Nearest neighbor gives you the most detail, cubic convolution blurs your data the most. The UTM, Universal Transverse Mercator System. You need to be able to explain a lot about this, like it's based on a transverse Mercator or cylindrical projection. It rotates around that minor axis, thus dividing the world into 60 zones, 6 degrees wide. Distortion is minimal within each zone. You want to make sure that maps for different areas use the zone that they are in. And the best map, this is the best map for covering small areas that are all inside of an individual zone. You need to know that on-the-fly projection does not project anything. It simply takes data, reads the projection and coordinate system that is there, and displays the data together seamlessly. It does not change the projection. You need to know the difference between the project tool and the define projection tool. The project tool takes an existing data set with a known spatial reference or coordinate system and projects it to a new projection, creating a new file. If you're trying to project data, if you don't end up with a new file, you use the wrong tool. The other tool is the define projection tool. The define projection tool is essentially a label changer. It takes a coordinate system or projection and it redefines that. All it does is erase the existing name and put in a new name. And so it doesn't change anything. If you're trying to correct a projection that is labeled incorrectly, you would use this tool. If when trying to do that you end up with a new data file, you use the wrong tool. The caution is just there to make sure you understand the gravity of not using the wrong tool. You need to be able to explain the process of geo-referencing. You take an image and you take another image that has a spatial reference. Then you identify common locations between the two and identify the coordinates at those locations. You can either then enter those coordinates for the locations of the unreferenced layer, or you can simply establish the links between the referenced and the unreferenced layer and then update the geo-referencing or rectify the image when you're done. And that's sort of the whole process. You'd be able to describe that in some detail. Give me a couple of sentences there. If I were to ask you, how does geo-referencing work? You should be able to tell me. Differentiating things on maps. If I were to ask you, how can you make data appear differently on maps, you should tell me the You can do it by changing shapes, by changing sizes, by changing thicknesses, by changing line types, by changing colors, by changing patterns, by changing font, by changing the font color, the font style, etc. Need to know what the modifiable area unit is. If you can tell me that it is caused by the arbitrary aggregation units like states or counties and how that influences values, we'll be pretty good.